Let's talk about pathfinding. There's surprisingly low attendance today. This lecture, more than any other lecture, is going to prepare you for that last homework. So seeing low attendance, well, doesn't bode well for the people who aren't here. I guess you can watch the videos and stuff, but hopefully they do. But I want to start off just by showing the last homework, some things about this. So with the last homework, with the code you've been given in lab, you should be able to run the server, let that fire up. Waiting, here we go. Go into your GUI. And we want to be able to click, just to make sure it's absolutely clear what we're doing here. I want to be able to click and have that move to where I clicked. That's our goal, and at least move to the tile which was clicked. So we want to be able to find that path and then move along that path to be able to find that tile. And the homework doc is out if you haven't noticed it, if you haven't seen that yet. I released it Wednesday. There are two methods in the homework. One, to compute the path, given a start and end point in a map. And one, to be able to take that path and your current location and figure out which velocity you should have to be able to travel along that path to the end point. Once you have those two methods written, you should be able to do what I just did here, fire up the server, open up the HTML in the browser, and be able to play around with this and test your functionality. So the big thing here is that we have general pathfinding. So right now I've just been in this little almost island here, but if I click over here, we're going to be able to find that path to move around all that water. You have to use your imagination a little bit on the visuals here, but to move around that water and be able to find that path to get to wherever was clicked. So we should be able to move around all that. So we want general pathfinding, and like I said a few times, even if this level were designed as a complete maze, this would be a general maze solver in the end. You have a question?
So velocity is constantly changing. Does the velocity update after each square?
The velocity updates. The velocity updates every 33 milliseconds. We're sending an update and getting the new velocity. So that method's called once a frame with 30 FPS on this one, the way it's set up. And you can adjust that. If there's lag or something, you can change this value. So get path is called on every click, and then that path is stored, and then get velocity is called every frame to get the new velocity. The last part of this, this is only for the bonus, so for those of you who will do the bonus, if I do a diagonal movement here, right now I don't have the bonus implemented, so I have a lot of kind of zigzagging back and forth. I'm only moving up, down, left, right. For the bonus, if I click a diagonal, it should move diagonal that entire way. I just don't have that code running on this one quite yet. But you should have that path smoothing. And with the bonus, I'll talk a little bit about this. Can I set one up here? So the bonus is a little bit deceivingly difficult. It's very difficult to do that smoothing. So you might think, okay, whenever I have a left and then an up, I'll just change that to a diagonal, for example. But what happens when you have what I showed over there, when you have a very long diagonal? Well, you could smooth that whole thing out. That's fine too. But what happens when you have a fairly long diagonal with a water tile right in the middle of that diagonal? How do you smooth that one out? So if you're looking for that bonus, if you're starting to think about that far ahead right now, that's the big challenge, is how do you flatten out a diagonal? How do you diagonalize that when there's water right in the middle of a long diagonal? That's what makes that bonus really tricky. All right, so how are we going to do this? This is what we want to talk about today. how are we going to accomplish that pathfinding? Of course, we're going to use BFS. It's in the title. Oh, and just in case that wasn't clear enough, with the grader isn't up yet. I'll be working on that this weekend. But to test your code, you can go into your GUI, fire up your server, go into the GUI, and click around. It's probably the best way to test this one. If you click and the thing moves to where you're clicked, I mean, you got it. You're there. You might have some things that still need to be smoothed out, some edge cases and stuff, but you have very visual feedback on this one to see what you're doing. And for the first objective, you have to write your own test cases anyway, so, but I'll get that grader up. But you have visual feedback on this one, which something I like in homeworks when you can get that feedback. Anyway, pathfinding with BFS, how are we going to accomplish this? The lecture question today, kind of the halfway point between the homework and the last lecture question. Find the distance between two nodes. On Monday, I asked you to compute, are these two nodes connected? So does there exist a path between them? Now I want to know what's the distance between them. So, and we'll define distance more formally in the slides, but it's the length of the shortest path between those two nodes. Then for the homework, you have to compute that shortest path and actually return one of the shortest paths between those two nodes. There can be a lot of shortest paths that are tied for length. So find the distance between two nodes. And you can see it, but 20 points due Sunday, so you get a few days to work on this one if you want them. Though I recommend just knocking it out tonight, getting it done. All right, so path, we saw the definition of a path. This is a list of nodes where any two adjacent nodes in the path are connected by an edge. So we have this path, Lincoln, MIT, Utah. We have this path through the graph. This is a valid path. It's all connected. And now we want to talk about the length of a path. We want to talk about the shortest length path and things like that. So let's define the length of a path. It's the number of edges in the path. So how many edges did we have to travel throughout that path? This is a path of length 6 because there are 6 edges. There are 7 total nodes. It's the length is the number of nodes minus 1 or the number of edges. Depending on what information you have your hands on, either one of those might be easier to compute. So this is a path of length 6 through the graph. Distance between two nodes is the length of the shortest path between those two nodes. So we say Lincoln and SRI. These two nodes are distance 3 from each other because the shortest path between these two nodes has length 3. So we can go Lincoln, MIT, Utah, SRI. 3 edges to get from one to the other, but there does not exist a shorter path. There are no paths of length 2, there's no paths of length 1. That's the shortest path between Lincoln and SRI, so the distance between those two nodes is 3. RAND and BBN, these are connected by an edge. That's the quickest you can get from one node to another is if they are connected by an edge. That's a path of length 1, that's distance 1 between those two nodes. That's the shortest distance you can have. Unless you're talking about the distance of a node with itself, we would call that distance 0. About two different nodes, the shortest distance is 1 if they're connected by an edge. If they're not connected by an edge and they are connected through a path, then you can have larger distances there. So a path, the length of a path, and distance, kind of our new vocab words. Path we've already seen, but distance and length of a path are important for our discussions. So now, with those definitions in mind, let's use BFS to be able to find the shortest path and distance between two nodes. We want to do pathfinding. That's the whole goal of this last homework. How do we use what we have here? We have graphs, we have BFS, we have this idea of a grid-based map and locations with physics vectors and things like this. How are we going to combine all of that to solve this pathfinding problem? So let's take a look at BFS again. Let's see another run of this. And instead of just going through the BFS like we did last time, I want to track some extra data. We're going to go through BFS a few times here, I believe 3 times, and just track different information each time and see what kind of information we can extract throughout the run of this algorithm and how we can maintain this information to be able to accomplish our goals here. So let's run through this. Instead of just running through the algorithm, I'm going to highlight the nodes that we were exploring. And just to change things up, I've been starting at UCLA. Just to change things up, we'll start at Carnegie this time. So let's start at Carnegie and look at what we're doing when we're navigating these this algorithm, and let's track the paths that we've traveled during BFS. So let's start at Carnegie, and I want to just say, okay, I'm starting at Carnegie, and let's build a second graph with only the edges that we've traveled, that we've explored during the run of BFS. So when we start at Carnegie, we're going to explore anything that's connected to Carnegie that we haven't yet explored. So I'm going to mark Carnegie orange to say that we've explored it. I would have some map of nodes to booleans to say, yes, flip that to true, I've explored this, or a set like I did in the code, put that in the set. Some way of marking this as explored. And I want to go to its adjacency list, check out everything it's connected to, and visit every node that I haven't yet explored. So I'm going to visit Case and Harvard, taking these two edges, and I'm going to add that to this second graph that I'm building as I visit them. Now I want to go to Case and Harvard, and I want to explore their edges. They have an edge to Carnegie that's already explored, so we ignore it, but explore Lincoln and BBN. And just keep exploring the neighbors of the nodes that I've just explored. So I'm going to BBN and Lincoln now. And I have one choice here. MIT is going to be discovered by both of those nodes at the same time. So I can choose one of those edges arbitrarily. So whatever one, and in the code, it's just whatever one was added to the queue first, just the way the adjacency lists and the graph was built will decide this arbitrary decision for us. But whatever one we visit, check out first, Lincoln or BBN, that's the one that we'll visit MIT through. So we'll just say that the code ended up exploring that through Lincoln for this. But we would not add both of those edges. If we explored Lincoln, explore MIT through that, add that edge. When we check out BBN, MIT is already explored, so we would not move over to MIT. So we had an arbitrary choice of which edge to choose, and we're just going to let the code figure out whatever one explores MIT first, that's the edge we'll choose. Now, Rand and MIT, we're going to add all of the edges, all of the nodes that we can explore from those two nodes, and all the nodes that we can explore from those nodes. And again, SRI had a lot of arbitrary decisions. I shouldn't say a lot, but it was UCLA, UCSB, and Utah all could explore SRI. So we just had to choose one arbitrarily. Utah, we'll just say that that's the way our code was set up. Utah happened to explore that one first, so we're taking that edge and not the other two because they were already explored when we checked out these nodes. And Stanford had to come from UCLA. All right, so now that we have this new graph, let's see what we actually built here. What did we do here when we built this new graph in such a way? Now, we noticed the only thing we did from the original graph to this graph was remove a few edges. There were a lot of edges that we ignored because that node was already explored. And when we build a graph in this way, we actually end up with a tree. A general tree is just a graph with no cycles in it. Slightly different from the binary trees that we explored. Those were rooted binary trees, slight differences. But what we have here is the definition. We have a graph with no cycles in it. So since we have this, a connected graph with no cycles, if you're really picking my words apart. So we have this graph with no cycles. And just the way I drew this, we started at Carnegie, explored all its neighbors, explored all their neighbors, explored all their neighbors. And I set this up visually for each to have the branches fall down from Carnegie. Anyway, what we get with this structure is levels to the graph. We have wherever we started at level 0, its neighbors at level 1, their neighbors at level 2, and then each time we explore a new set of nodes, we're going to create a new level to this tree. And we finally get the payoff here. Whatever level number a node is on, that's its distance from our starting node. So we get exactly the distance just by tracking these level numbers as we go through BFS. And I'll do a quick kind of hand-wavy proof. So suppose there were a shorter path between, let's say, Carnegie and SRI, if there were a shorter path between these two, the algorithm would have found it because it's always exploring every node that it can find with paths of one greater length. It's always exploring every possible path that it can find. So if there were a shorter path from Carnegie to SRI than this path that we found, the algorithm would have found that path instead of the one that it found here. SRI would have been explored earlier in the algorithm if there were a shorter path, because it would have taken that path, because we're exploring every neighbor from all of the explored nodes. So these levels give us the distance directly. So we can use the structure of BFS to start extracting more information out of this graph, out of the nodes, and compute things like distance. And the next thing we want is pathfinding, the paths, the shortest paths between any two nodes. But I have one big question, you should too, is that's great visually on a slide, but how would I code that up? How would I track these levels as I'm running through BFS? How would I do that? And there are multiple ways to do this. There are different ways. If you hacked at this for a while, you'd probably come up with a different way than this. Well, let me just show you at least one way where this can be done. I'm going to have a map of nodes to distances that I'm going to track as I run through the BFS. I'm going to initialize my starting point as 0. That's at level 0. And the distance from a node to itself, we'll call that 0. And then every time I explore a node, that's my queue at the top. I'm going to add Carnegie to my queue. That's the nodes that we're going to explore. When I dequeue Carnegie, I'm going to visit all of its neighbors that haven't been explored yet. And update, whenever I explore a node, I'm going to update its distance as 1 plus the distance of the node that I used to visit that node. So I'm currently visiting Carnegie. I'm exploring Carnegie's neighbors, I should say. I find case. So I'm going to look up, okay, case distance is going to be 1 plus Carnegie's distance, which is 0. So I add a 1 in that table and mark it explored. Now I'm going to visit case. I find Lincoln. I found Lincoln through case, so I'm going to add 1 and update my map. In my map, insert Lincoln to 1 plus where I came from to get 2 in that map, to mark that distance. And when I explore Lincoln, add that to the queue because I need to explore its neighbors next. And we can see the importance of using a queue here, and that I don't want to explore Lincoln at distance 2. I don't want to explore that before I visit a lower distance node, Harvard, of distance 1. If there were an edge between Harvard and MIT, I want to make sure I find that path and not this path. And the queue keeps everything in order in the way that we want to be able to get these properties out of the BFS algorithm. So I'm going to explore Harvard before Lincoln. And in fact, the queue will always maintain that. We're always going to explore, we're always going to be monotonically, what's the terminology? Non-decreasing in the distance of the nodes that we explore the neighbors of. So I'm going to explore Harvard, add BBN at 1 plus 1, add BBN to the queue, explore Lincoln, add MIT to the queue at 2 plus 1, 3, and add MIT to the queue. Explore BBN, and this is where we would ignore this edge because MIT is already explored, but we're going to visit Rand, MIT, and push Rand onto the queue, or in queue Rand. DQ MIT, visit Utah, add Utah, visit Rand, add all these, all at 3 plus 1. Visit Utah, SRI, visit UCLA, 4 plus 1, and we have all of our nodes explored. And then we go to our queue. These are all, we've already visited all these. Our code will look through their adjacency lists, see that everything's marked as explored and not actually do anything. So we pop those one at a time without actually updating any values because all of their neighbors are already explored. And now we have a map that's going to store the distances from the starting node to every other node in the graph. We have all of their distances by tracking one extra data structure throughout the run of BFS. So like I said last time, the BFS that I gave in the code, that's to give you a good idea of what BFS is doing, how to implement it. You'll have to do some heavy modifications to it to be able to complete the homework, and some more, somewhat slight modifications to complete the lecture question today. I gave that BFS as a starting point, and you should be able to apply that with these ideas in the slides. I won't go through code to do this. That's your job at this point. So, but if you add a map of nodes using their indices, so ints, a map of ints to ints representing the distances, initialize the starting point to 0, and then constantly update every time you explore a node to mark that node's distance. Now we can get the distance from the start node to any node in the graph. Any questions at this point? So up to here, this will get you through the lecture question today by adding this map, updating those distances when you explore nodes, and returning the distance that you found for the one of the nodes. So you're given 2 nodes as indices. What's the distance between these 2 nodes? Choose one of them as your starting point for your BFS. One is your ending point, and then run your BFS with this added data structure and return the distance of that ending point. That's your distance between those 2 nodes. And BFS will guarantee that that is the shortest distance, as long as you're in queuing and doing everything in the right order and not overwriting data and things like that. BFS will guarantee it. There are proofs that you'll write and you'll see in 331, proving that that is always the case, always the case. So this is cool and all. We got the distance. That's going to get us through today's lecture question. But what we're really interested in is the pathfinding. Now, we know that we did travel those paths. We did travel the shortest paths through the run of BFS. But how are we going to extract those paths? How are we going to maintain those paths? I'll show you a way here. Again, this is another thing where you would figure this out, hacking long enough eventually. But I want to show you how we can use a data structure to be able to store information and be able to compute these paths a little more efficiently, a little cleaner in the code, more likely. It'll be fewer lines if you follow something like this. So we can get the distances using this data structure of mapping the nodes to ints. In the code, it would be ints to ints, node ID to distance. But how's that going to work for paths? Let's take a similar idea as the path, but instead of storing the distance as an int, we're going to store the previous node in the path, or the node that was used to explore another node. So for Carnegie, we're going to mark this as the start. We'll just have some special way of indicating that this is the starting node. And then every time we explore a node, instead of marking the distance, instead of saying distance of where we came from plus 1, we're going to store the node we came from directly. So Harvard and Case, we're going to say we were explored through Carnegie, so let's store Carnegie in our previous node's data structure. So we're mapping nodes to the node that discovered it. When we go on to our next step, BBN in Lincoln. BBN was discovered through Harvard. Lincoln was discovered through Case. MIT, we discovered through Lincoln. RAND, we discovered through BBN. So we're just tracking where we came from each time we explore a node. And for the rest of it, we're just going to do the same thing. Instead of adding 1 to the distance of where we came from, just store the node where we came from directly. So this again would be a map of instance, but we're node ID to node ID. Where are we going? Where did we come from? Okay, so how does this help us? And this is the only extra information you would store in your run of BFS to be able to get the paths. But how do we get the paths from this? You are hopefully asking, unless you know, unless you can see it already. So how do we get these paths? So we started at Carnegie, so we know Carnegie is one endpoint to our path. So how do we compute the path from Carnegie to Stanford, for example? So for this, we're going to start at Stanford and work backwards. So Stanford, where did we come from? UCLA. Now we have a path. It's ending in Stanford, and the previous node from Stanford was UCLA. Now we're going to look up UCLA. Well, where did you come from? I came from Rand. Rand, where did you come from? BBN is my previous node. That's how I was explored. BBN, where did you come from? Well, I was explored through Harvard. Harvard, where were you explored from? Carnegie. Carnegie, where were you explored from? I'm the start of the path. I'm the starting node. And now, so by starting at the end point, our destination of the path, and then working backwards by continuously looking up the previous node in the path, we can get a shortest path from any node in the graph to the starting node of our BFS run. And again, we're guaranteed, since we do get the shortest path, we get the distance through this, this is guaranteed to be a shortest path. There may be ties, we broke some ties arbitrarily, there may be other paths that have the same length between the two nodes, but this is a shortest path between those two nodes. All right, any questions on that? So this is a way we can store extra data structures to maintain some data throughout the run of the algorithm that we can, and then use that data later. So any questions on this, on pathfinding? This is really the last topic of the course, so that's about it. There's one more thing you may be thinking of. You should be thinking of at least. Okay, that's great too. We had a graph and we computed the shortest path between any two nodes. But that's really not the problem that we're faced with on the homework. We don't have a graph, we have a game board. So how does this help me? Why would I care about the shortest path in a graph when that's not the problem I'm faced with? I'm faced with shortest path between 2 points on a grid where some of the tiles are passable and some of them are not. Very different problem. So how does that help with this? Where for this game, these are our walls. We can't pass through these. These are our impassable tiles. And giving a start point and an end point on this map, how would we compute the path to go from point A to point B without moving through any impassable tiles? The short answer is we're going to turn it into a graph. So we have a solution for graphs. We have a problem in grids, so we're going to change our grid into a graph. So for this, we'll think of each node, each tile in the grid as a node in our graph, and connect any two adjacent tiles as long as neither of them are impassable. So when we have our impassable tiles, they have no connections with any other nodes. Or if you want to get, or when you create the graph, you can just omit those nodes entirely. They really don't affect the pathfinding at all. But you definitely wouldn't have connections to nodes in these locations, but you do have connections in any direction that a player can travel. So if we can go up, down, left, right, we're going to make those connections. And now we have our graph. We'll have a starting point and an end point in this graph. We can run BFS to find the shortest path, and then return that path as the path that should be traveled.
Since we can move diagonally on the homework with the additional connections between each node, diagonal is going sort of either direction, including up and down.
Yes. So if you're thinking of the homework and you have these diagonals that you can take, there's a few options here. I want to talk about this. Before I talk about that, because I'll go off for a little bit on that one. Any other questions on the graph structure and the setup and everything? Okay, so if you're thinking the bonus question, you're thinking, okay, I can use this find, if I'm going from here to here, I can find this path and then smooth it out with the diagonals wherever they can go. But why would I do that? Why would I not just add in the diagonal edges and then run BFS? This is a very important question because those edges do not have the same length as these edges. So every edge in this graph has the same length. Every edge is exactly one tile long. So we can run BFS, which is going to find the shortest path in terms of number of edges. But once we have edges that have different weights, once we add in diagonals that are root 2, that took me way too long to think of, that are root 2 length. My mind was like, no, root 2 is less than 1. No, it's not. Anyway, we have edges of root 2, of length root 2, and edges of length 1. Now, BFS is going to find the shortest path in terms of number of edges, but that might not necessarily be the shortest path overall. And I'm trying to think of an example where that's the case. Maybe it will just get away with that. I have to think about that some more. You might actually get away with that for this.
It's like if you had like a water tile in the way of it, then like the shortest path would almost be like a splash diagonal most of the time with like a curve in it or something.
Yeah, I'll have to think about that one more. I know, and just to clarify part of the question, there wouldn't be an edge between these two. You wouldn't be, you can't go if there is a impassable tile as part of that thing. But I'll have to think about that. You might get away with it. If you do, let me know. If you do get away with just adding the diagonals, that's not a valid solution. If the edges are different weights, BFS does not always find the shortest path in terms of sum of all the weights. I don't know why I'm blanking on an example. But if I come up with one, I'll talk about it on Monday. But in general, that's where we would use something called Dijkstra's algorithm, which you'll learn in 331. But I'm failing to come up with the counterexample here. I'll think about it. And this is very common with algorithms, with software in general. As humans, this is what we want to see in the view. We want to play a game. This is the game. This is the last homework from last semester, the visual here. That's what we see when we're playing the thing. Computer's going to see something completely different. So if the computer is this dot right here, and for this example, they were an AI trying to find the enemy base, the computer sees this. I'm right here. I need to be here. I need to run my DFS algorithm and go through this level. They're going to see this completely differently than a human sees it. So big question in a lot of algorithms is, how do we take the data that we have and represent it in a way that the computer is expecting to be able to run our algorithms on this data? It's all data representation. How do we represent the data and use our algorithms on that data? All right, any other questions? Well, so I'll have some time to answer questions. If anybody has them, come on down. Other than that, have a good weekend.